Okay, hello and welcome everyone. In this video, I'm going to walk through a couple microeconomics exercises, maximization problems, consumer utility maximization problems, specifically for these preferences right here, question number 13 that I've got here, for this Cobb-Douglas one, question number 14, for this quasi-linear one, question number 15. Might as well do 16. This is a perfect complements question. 17 is the same as 15, so I don't need to do that one, actually cross that one off. 18, that's a Cobb-Douglas one, do that one, and then question 19 is another Cobb-Douglas one, and then I'll stop at 20. That'll be another video. So that'll be the plan as long as things go according to plan. Otherwise, I'll just pick those up in a different video. All right, so Ann's preferences are represented by utility coming from whichever is the smaller of the sum 2x and y and the sum x and 3y. Given prices and given the prices, her optimal bundle is an interior solution, meaning there's a positive amount of both x and y. So now sketch Ann's indifference curves, labeling only the MRS, above and below the line through the IC's kink. Find the open interval corresponding to possible values for the MRT. Remember, the MRT is just the price ratio. All right, well, the first thing is this is like complements coupled with substitutes. So we have kinks, but we also have the wings of the Leontief or complements indifference curves have slope to them. And so that's captured by this aspect right here. We can still find the line that goes through the kinks. And so that's just going to be found by replacing this comma with an equal sign and solving for y. Okay, so if we solve for y here, let's see, we move x to the other side, that'll just be 1x. Move y to this side, that'll be a 2y. So it's going to be y is equal to 1/2 x. It's going to be the line through the origin going through the corner. So I said Ann's indifference curves are not right angles. They're relatively steep with a slope of 2 above the line, y equals 1/2 x, relatively flat with a slope of 1/3 below the same line. How do we know that? Well, this is going to have a slope of 2. Think of like how we'd find a normal MRS for subs, right? MUX over MUY, that's MRS is 2. Here this is going to be MUX of 1, MUY is 3, so the MRS is going to be 1/3. So it's going to be steeper above, flatter below. I wonder if I had a picture. Do I have a picture? I do have a picture. Beautiful. All right, so here is going to be the picture. The MRS is 2. MRS is 1/3 down here. Yeah. This should be negative. This should be negative here. But we know they're downward sloping, and so we know the MRS is always negative. But let's not worry about that pesky negative sign. And so oftentimes we just report it an absolute value. But if you want to draw a negative there, you want to draw a negative there, good. You can do that. And you'll have to draw negative for the budget constraint, which the px over py, which I'm also going to report an absolute value. Anyway, so here's going to be the line through the origin. Y is equal to 1/2 x, good. And then above the line through the corners is going to be the higher slope, and below is going to be the lower slope. So to get an interior solution to be somewhere along here, think about what the budget constraint's going to do. Think about the budget constraints got to do. Well, the budget constraints got to have a slope that is less than 2, but greater than 1/3. That's my comment here. In order to get an interior solution, sum of both, we require that the price ratio of the budget constraint, slope of the budget constraint, lies between 1/3 and 2. Now, I said open interval. Why did I ask for the open interval? We go back up here. I say, okay, open interval. Find the open interval corresponding to possible values for the MRT because we want an interior solution. The reason why I'm requiring an open interval is because if I allow the closed interval, if I include the endpoints, that could involve a budget constraint it would involve a budget constraint that's coincident with this indifference curve or this indifference curve, where the price ratio is exactly 1/3 or is exactly 2. And the problem is that budget constraint and that indifference curve can cross all the way up there at the axis and all the way down here at the axis. So we wouldn't guarantee an interior solution because you could find a corner solution that's perfectly consistent with the price ratio being equal to 1/3 or perfectly consistent with the price ratio being equal to 2. So to rule that out, I require the open interval. So my comment is this is ruling out the all x and all y solution. All right, so that was this right here. Let's see, is there anything else I wanted to say? No, I don't think so. Yeah, I should just say if MRT, if the price ratio equals 2 or the price ratio equals 1/3, there is a continuum of solutions, meaning anything, if the budget constraint and the indifference curve have the same slope, anything along there is optimal. Okay, so Then I want to do question number 4. So these are Cobb-Douglas preferences. Budget constraint is 2x plus 3y is equal to 20. Write down the maximization problem, compute the MRS, find the optimal bundle. So here's the Lagrangian. It's a function of x, y, and lambda. So here's my objective function. That's just the utility function, minus lambda, and then here's the budget constraint, 2x plus 3y minus 20. Okay, good. Now what I'm going to do is I'm going to take the partial with respect to x. So if I take the partial here to get me mux, that's going to be 2/5 x, reduce this power by 1. So it's going to be 2/5 x to the minus 3/5. The y to the 3/5 comes along for the ride, so that's there. And then I'll take the partial of this portion. That's going to be minus lambda times 2. That's just the coefficient on x equals 0, makes it our first order condition. Then I'm going to take the partial with respect to y. It's going to be 3/5. This 3/5 comes out front. Reduce this power by 1. So that's going to be, oh, I wrote this as 3/5. Oh, that's disappointing. Hey, I had this thing though. This needs to be, it's not going to let me do it, is it? That has to be a 2. That has to be a 2. All right, so of course, like when I'm trying to fix it, then it doesn't work. Hey, look at that. I made this arrow that was not a straight line because I didn't want a straight line, and software changed it so that it's straight line. Okay, so that's got to be minus 2/5 here, right? Because we're going to take this power down, 3/5 out front, reduce this power by 1, and so it's going to be minus 2/5. All right, anyway, so then don't take the partial with respect to y here, so it's going to be minus lambda times 3. Good. We're going to solve this system of equations. Notice this is the MRS, right? This is MUX divided by MUY. Almost my arrow sign's almost making that ratio bar. And this is my price ratio, minus 2/3 or 2/3, right? Well, what this boils down to is if you think about this division, this is going to be 2/5 divided by 3/5, 2/5 times 5/3 or 2/3. What's going to happen over here? It's going to be minus 3/5 minus 2/5 because you have the same base, you subtract the exponents. So it's going to be minus 3/5 minus 2/5 is minus 1, but minus 1 in the numerator is the same as plus 1 in the denominator, so x goes down here. And then for y, it's going to be 3/5 minus 2/5 or 3/5 plus 2/5 or 1. So my MRS is going to be 2/3 y over x equals 2/3 from this right here. 2/3 here, 2/3 here, those cancel, x is equal to y. Let's plug that into our budget constraint. So this becomes 2x plus 3x. Why? Because the budget constraint would have been 2x plus 3y. So it's 2x plus 3x is going to be x, or 5x is equal to 20, or x is equal to 4. If x is equal to 4, then y is equal to 4, and that's how we got our optimal. Let's see. Are they substitutes or complements? Well, neither, because here's our Cobb-Douglas demands. Notice, for substitutes, you'd need the demand to be increasing in the price of the other good. If the price of Pepsi rises, you buy more Coke. If they're complements, the demand needs to be decreasing in the price of the other good, but py doesn't appear here, only px does. And px doesn't appear here, only py does. So we'd say they're not technically either substitutes or complements. Both depend only on their own income and their own price. And so they're not really substitutes or complements. I mean, there's some substitutability and there's some complementary, but not in the sense that we've defined. All right. So that was 13. That was 13. Nope, that was 14. So we did 14. Oh, we have to do part C. So I'm trying to have these pictures, but then it takes up the whole thing. So, all right. So suppose the price of good Y increases by a factor of 10. Find X. Find the optimal X. Look at our Cobb-Douglas demands. Suppose the price of good Y increases by a factor of 10. What happens to my demand for good X? My demand for good X is invariant to changes in the price of Y. Price of Y could change by 1,000,000, and I'm not going to change my consumption of X. So my demand for X is still just 4. Py has no effect on X. What proportion of my income, or does Annan's income, spend on X? Well, remember the fraction of income we were getting from this. So here's our Cobb-Douglas demand. You can move Px to this side, and you get Px. You'll get Pxx, which is this. That's the expenditure on X. And then you'd move Py here. That's the expenditure on Y. And it comes down to just whatever is that coefficient. What was that coefficient here? We had solved for. It was, oh, we didn't. No, so we'd have to do the alpha over alpha plus beta. If you do that, let's see. Alpha was 2/5, so it's going to be 2/5 m, and then beta was 3/5, so it's going to be 3/5 m. So so point 0.4, 40% of my income, of Ann's income, they're spending on X, and 60% of Ann's income and spending on Y. That's just from 0.4 and 0.6. All right, so Bob's preferences are represented by these quasi-linear preferences. Find the marginal rate of substitution. We'll take the partial with respect to X, that's just 1, that's MUX. Partial with respect to Y, that's 1 over Y. Why? Because the first derivative of the natural log function is just 1 over the argument. So derivative of ln x is just 1 over x. Okay, so then, yep, marginal utility of x is just 1. Marginal utility of y is 1 over y. 1 divided by 1 over y is y, which is equal to our price ratio. So find Bob's demand, y star, demand function, consuming, y depends only on the marginal rate of transformation. Why? Because we're going to get y is equal to px, because we had MRS is just 1 over y, which is just y. Set that equal to the price ratio. That's px over py. So Bob's demand for good y is just the ratio of the prices. It's just the price ratio. So we say y star is px over py. Find Bob's demand function for good x. Well, to do this, we're going to have to plug this in for y into our budget constraint. So the budget constraint is the expenditure on x plus the expenditure on y. Here I've replaced y with px over py. We cancel the py's, and we're left with pxx plus px is equal to m. You could factor out the px, and we end up with, no, we don't want to do that. So you subtract px from both sides. You have m minus px divided by px. That's what we want to do, and you'll get x star is equal to m minus px over px. Moreover, Bob's not going to begin buying good x until m is bigger than px, because otherwise Bob's not going to be able to afford y. So that's my comment down here. Suppose px is bigger than m, py is bigger than m. Find x star, y star. If the price is bigger than the income, Bob's unable to purchase x, therefore only consumes y, a corner solution, and exhausts Bob's budget on good y, m over py. When the price of both goods exceeds the budget, is able to consume some fraction or share of y, x is completely unaffordable. Remember, with quasi-linear utility, the consumer is fixated on one particular product. In this case, for Bob, it's y. And so Bob's going to make sure that Bob gets exactly px over py units of good y before Bob begins buying x. Once Bob has this amount of y locked down, Bob's not going to buy any more y. Question 16. Did I tell myself? Yeah, I was going to do these. Bob always consumes exactly alpha units of x with beta units of y. Write down Bob's utility function. So the preferences are indeed ux of y is equal to minimum beta x alpha y. You might have thought, oh, alpha x y beta. So you might think of like it's this alpha x and beta y. Remember, in the choice examples video and in lecture, I've got this example where I said, oh, right, so suppose Bob always consumes 2 cookies with every 1 coffee. Let's list all the bundles that Bob would find acceptable. Literally 2 cookies, 1 coffee, 4 cookies, 2 coffee, 6 cookies, 3 coffee. This gives rise to x being x, 2 being twice y, right? 2 is 2 times 1. Replace the equal sign with a comma to get my preferences. Got it. Now we can think of this 2 and this 1 as beta and alpha. Whoops. 2. No. This 2 is to 2y as 2 is to 2y as alpha is to alpha y. 1 is to 1x as beta is to beta x. Good. I was looking at this. I shouldn't even put this on here because it's... Anyway. So then we want to solve this. Suppose we observe Bob optimizing by choosing bundle 8.4. How are alpha and beta related? Well, to optimally consume a bundle with twice as much y, it must be the case that alpha is bigger than beta. To get twice as much y, it must be the case that alpha is bigger than beta. Because think of this. Let's put 8 in here. Let's put 4 in there. Then let's make alpha 2 and beta 1. That works. Alpha times 2. Alpha is 2 times 4 is 8. Beta is 1 times x is 8. So it's got to be the case that that alpha is bigger than beta. In particular, you could try alpha equals 2, beta equals 1. And just testing this here. So I've just replaced 2 and 1 and then this bundle. And I verified that they're the same on both sides of the comma. Suppose we observe Bob optimizing by choosing 4 and 8. Well, to optimally choose a bundle that has twice as much good x as y, it must be the case that beta is bigger than, twice as big as alpha. Beta is bigger than alpha. So now alpha is less than beta for the same reason. Plug in 4 and 8, plug in these betas with this thing, and you'll get the same. You'll get 8 and 8 on both sides. Suppose we observe Bob optimizing by choosing the bundle in the middle. Well, alpha's got to be equal to beta to consume the same amount. So let's just like alpha equal beta, and they're both equal to 1. Then I consume bundle 8, 8, and my minimum is just, my utility is just the minimum, which is 8. Suppose the price of good Y rises. What happens to Bob's demand for X? Price of good Y rises, we buy less of both, right? They're complements, right? Think of like perfect complements preferences. The demands are going to be X star, Y star is M over PX plus PY. If the price of either rises, the demand for both falls. They're complements. Suppose Bob's income rises, income appears in the numerator. As income increases, consumption of X and Y rises. These are normal goods. So if income rises, Bob buys more Y. Question 17, see question 16, it was the same. Sorry, I was moving things. I was trying to put things in order so that they're kind of in the order as covered in class and my other videos. Here's a Cobb-Douglas problem. Did I want to do all I think I did. I forget how many I said. I forget how many I promised I was going to do in this video, but whatever. So Ann's utility function, Cobb-Douglas, x to the 1/4, y to the 3/4. Income is M. So the price of good X is PX and the price of good Y is PY. What I did here is I just solved, just as we've been doing in the other videos, just taking the partial. So this is going to be 1/4 to the minus 3/4. Y to the 3/4 comes along for the ride. That's the MUX of Y. Sorry, MUX of Y. That's the MU of marginal utility of X. Marginal utility of Y is going to be this, to take this partial derivative, 3/4 X to the 1/4 comes along for the ride times Y to the minus 1/4. That's this right here. You could take the ratio and we'll get Y over 3X, which we couple with PX over PY to get our tangency. The other thing you could do is you could take a monotone transformation. So here I've log transformed this, so that if I take the natural log of this utility function, this becomes 1/4 ln of X plus 3/4 ln of Y, right? The natural log of a product is the sum of natural logs. Natural log of the product is the sum of natural logs. That's what this is. Okay. Then you take the marginal utility of X, that's 1/4X. Marginal utility of Y, that's 3/4 Y. Dividing, you get the M or S is going to be Y over 3X. Hey, that's exactly what we had down here. Set that equal to PX over PY and plug into the budget constraint. So here's my expenditure on Y is equal to 3 times my expenditure on X. Good. And then plug this into the budget constraint. So PXX plus PYY becomes PXX plus 3PXX, which solves for my demand for X is going to be M over 4PX. And then my demand for Y is going to be 3/4 M over PY. So here's the optimal choices. Here's my demand, my Cobb-Douglas demands. Alpha over alpha plus beta for X is my coefficient here. So 1/4 over 1 is, this is alpha over alpha plus beta is 1/4. That's where it's coming from. And then beta over alpha plus beta is my coefficient for Y. So beta is 3/4 plus alpha plus beta, which is 1/4 plus 3/4 is 1. So 3/4 over 1, that's this. Okay, times M over PY. Determine whether it's a normal inferior good. M income appears in the numerator. So if you take the partials of the demands, dx dm, dy dm, they're both going to be positive. Right, that's this right here. So they're both normal goods. Okay, use your solution to determine Ann's optimal choice when Ann has $32 in income, and these are the prices. All right, so 32 in the numerator, price 4 in the denominator, so 32 divided by 16 is 2. And then here we're going to have 3 times 32, so what's 3 times 32 divided by 8, yeah, 96 divided by 8, 12. All right, and so that's this right here. Oh, I wanted to do one more similar Cobb-Douglas. So here is, now I'll do the Cobb-Douglas with the Lagrangian. So Ann's utility is X to the 1/3, Y to the 2/3. You know what? You could probably skip ahead and you just be like, well, this is alpha, that's beta. My Cobb-Douglas demands are going to be, for X is going to be, X is equal to alpha over alpha plus beta, M over PX. So it's going to be 1/3 M over PX is my Cobb-Douglas demand. And then 2/3 M over PY is going to be my Cobb-Douglas demand for Y. Sure enough, that's these right here. How did I get this? Using the Lagrangian. Lagrangian's a function of X, Y, and lambda, so it's going to be the objective function minus lambda times the constraint, in this case the budget constraint. Take the partial with respect to X, so it's going to be 1/3 X to the minus 2/3, reduce the power by 1. and then 2/3 x to the 1/3 reduce the power by, sorry, 2/3 x to the 1/3 comes along for the ride, reduce the power by 1, it's minus 1/3. This divided by, this is my marginal utility of x, this is my marginal utility of y, this is my price ratio. So sure enough, my MRS is divide this by that. You get y over 2x versus px over py. This is just as before. My expenditure on y is going to be equal to twice my expenditure on x. Making that substitution, that's how I got my thing. I have no idea what that, I don't know what this is going to do. That's awful. Hey, I didn't connect it. I thwarted it. So I use GoodNotes on my iPad, which I use for literally nothing else than making these videos. And for whatever reason, there's some type of a virus or something in GoodNotes where it puts these ridiculous clickable things, and so it always has like some international web address. And so far, every single one that I've clicked on has been largely innocuous, but I'm sure at some point one of them is going to click through and be something that I don't want in my video. So thanks GoodNotes for your quality control. All right. So here's, okay, so whether x is a normal or inferior good, well, income appears in the numerator. So we take the partial with respect to income, gives us, well, a positive sign. So that tells us that both demands are increasing in income, hence these are normal goods. Let's see, then we want to determine the optimal choice when Anne has income 24 and when these are the prices. Okay, so I'm just going to replace income, replace prices. Optimal demands for both are going to be 4 and 4. All right, and that concludes here. You see this right down here. I'm going to do another video, and so that'll be the next video. Anyway, I hope you enjoyed. I hope you found it useful. I'll open up the comments. You can reply there if you have questions and or send me an email. And then hope you enjoyed.